idea is to understand what are the properties of matter that defines macroscopic properties. What I mean by that is we want to know how materials work and why they work and the way that they work. So one of the topics that I study are lithium-ion batteries, and the idea is to understand the molecular mechanism of the conduction of lithium electrolytes. The general idea is the following. You have a battery, and most of the people have a battery nowadays because they have a cell phone. In the battery, you need to have a conduction circuit between two plates, similar to what you have in a car with the lead-acid battery. And you need to have conduction in order to have electricity flowing through a battery and powering your phone. It's interesting that we have these batteries, but we really don't know the inner circuits and why it works molecularly speaking. And the idea is the following. It's not that we're going to change the paradigm of why these batteries work, because we know that they work. But it's the similar idea of what happens when you want to design a car. So if you want to design a car that works, you know the recipe and you can build one. Now if you want to design a car that goes at very high speed, like for example Maserati or a Bugatti or all these supercars, you really need to start describing what are the innards of the car in order to make it go faster. Okay, so if we want to build better lithium-ion electrolytes, we really need to start understanding how this system works on a molecular level. Otherwise, we're never going to go beyond what we know right now, that they work and they can do the things that they do.
Okay. Can you speak about your current research?
So that's where my research is focused on that. On that, we study these systems. So we build these systems. We have to work. Unfortunately, we have to due to the water problems. We have to work in a glove box and things like that. So we build our systems on a glove box in here in the lab, and then we investigate it and we look at how the different molecular parts of the system that makes the electrolyte. So an electrolyte basically consists of two things. This is the typical experiment that you do when you're a kid, when you turn on the lamp and you put, for example, water, and then you put two wires, and you see that when there is pure water, the lamp doesn't turn on. Now you put salt on it, and then what happens is that you put ions that conduct electricity, and the lamp turns on. So what we do is investigate why and how is the water moving in this system when you put salt, for example. Our system is slightly different. What we're studying are lithium-ion electrolytes, which instead of water, they have a solvent that is called an organic carbonate. And instead of having sodium chloride, they have a lithium salt. That is the one that you use to charge your phone. That's what we do. And then what we do is we look at what are these molecular motions, how fast the system is moving, and we look at how the structure of the organic solvent, the molecular structure on a very basic level, how that affects the different properties of the system on a very, very short time scale on a molecular level. And our idea is to try to understand the organization of the system such that we can bridge. I don't think that it's a problem that we can tackle by ourselves, but it's a part of the problem that it needs to be tackled in order to really bridge to a macroscopic level to see how the system overall works.
And how can what y'all study, how can that be applied to like just the normal guy on the street? Like how can that affect his life, make his life better, worse, etc.?
The electrolyte itself will not change how much conductivity you will have, and how much energy density you will have in a battery. That will not change. What it changes is how fast you can charge it. So do you want to waste like half an hour, or you want to waste 6 hours charging your phone? That's a question. So that it has to do with how much charges you move through the solvent through electrolyte when you're charging your phone. So if you really want to charge it fast, you will have to have an electrolyte that can move a lot of charges in a very short amount of time. That it has to do with the conductivity of the electrolyte. There is another problem, that is the safety of these batteries. It's known that the batteries are not very safe. The problem with the batteries itself is a combination of having lithium as an atomic element. So basically metallic lithium, it combusts. And the other problem is that the electrolyte is combustible too. So when you have a problem with the battery, you raise the temperature because of the lithium having a chemical reaction, and then what it happens is that they start combusting the electrolyte, and it's very hard to actually control that reaction. So you have two problems at the same time. So what we need to do, if we want to avoid problems like are well known about the lithium-ion electrolytes, we need to start moving to different electrolytes to make it more safe.
Okay, and so is that what y'all have been experimenting with, trying different types of electrolytes? And
Yes, we're trying to look at what are the properties of the electrolytes that make it good, and see if there are other families or other chemistries and why the different chemistries might not work, for example. What is the difference on the molecular level, such that if we understand what are the things that make it work or what are the things that don't make it work, then maybe we might be able to synthesize something instead of trying on trial and error the million different compounds that you can have nowadays to actually find out what is a good electrolyte.
now, I guess the experiments you do with the electrolytes, what devices do you use, or is it more computational, or like what exactly do you do?
So we do experimental physical chemistry where we put our samples in the laser and we measure properties of the system by doing this interaction with the laser. So we basically look at how fast the system moves through our laser system. That's the way that we start to describe the system on a molecular level. Then what we need to do is, because what we see basically is how fast the things change, but we don't have a molecular picture. So basically you can see how the things are moving, but you don't have a description of the system. Then we rely on computational methods to actually understand what is the basics of the things that are moving in there. And it's a very complicated task. It's not very easy for us to relate one to another, so we have to do a very complicated analysis on computational methods like molecular ion simulations.